Hello everyone, welcome to Digital Media E10. This is week 8 where we get to talk about digital cameras. So a lot of the topics that we had addressed in prior weeks really can apply to not just digital photography but also regular photography. Obviously exposure is something that we can use with any type of camera regardless of whether it uses a sensor or film. And even when we were talking about organizing photos or editing them, it still is possible to use a film camera and, say, scan them into your computer and still organize them or edit them that way, although we didn't really talk much about scanning. So today, though, is the first of 2 weeks where we get to talk about topics specific to digital cameras. And specifically, we'll get to talk about their sensors, some of the differences between sensors, what that means for us, and ultimately how this impacts our raw images, what a raw image actually is and why it is the way it is. But before we dive in, I just want to do our weekly announcements and assignment reminders. So just as a reminder, Project 3 is due tonight at 11:59 p.m. This is the group project and should be hopefully wrapping up in the next couple of hours. Problem Set 4 is due next Wednesday, October 29th at the same time. Project 4, which is the final of the numbered projects, is released today. So there's 4 numbered projects, Project 1, 2, 3, 4, and also the final project. And Project 4 is the last of those, and the spec has been released. And so I do just want to talk a little bit about that, just as I have in prior weeks talked about some of the other projects as well. This one really is a lot looser in terms of what we are expecting. And what I mean by that is, with Project 3, really the idea was to take a series of photos and then edit them. Project 2 was to have a big project and accomplish that. Project 1 was trying to capture shapes in your environment. But the requirements, at least in terms of what we're hoping that you will capture, are a lot looser for this one. And in particular, this project, we're hoping to ask you to capture images that will be exhibited or potentially exhibited in a number of ways. One of them is an image for the website. So in part 1 of the project, we ask you to capture an image and to submit it in multiple resolutions that can be used on the course website. And there's some additional criterion that are available on the project that I encourage you to read through and make sure that you understand. In particular, we're very in order to actually use the image on the website, it has to be submitted in 2 very precise resolutions. So do be sure that you pay attention to that as well. But really, whatever image you would like to produce is certainly fine. And for this first portion, the portion for the image on the website, we're hoping that you will, and we're expecting that you will take a new photo. So one that you have not yet actually taken, one for the purposes of this. And of course, because this is a publicly accessible site and publicly available to actually see your images, please do be sure that you take that into account when you're actually capturing the image. So one that would be appropriate for the course website and so on, so in order for us to actually use it. Now, one of the things that you may have noticed about the course website is that we do, in fact, as you reload it, you get different images depending on which, on just random chance, really. And right now there are 45 images that are here, and we hope to greatly expand that based on the images that you provide to us. Now that's only about 20% of the project. The bulk of the project are images that we are going to hopefully use at the end of the course's exhibition. So at the very end of the course, we'd like to have a local exhibition, and I realize that it will be a little bit more difficult for those that are afar to actually participate. But still, I think there's something that's kind of neat about having people's photos, no matter where you are in this class, being hung somewhere. You know that they're actually being physically hung and shown in some location, whether it be on campus or off campus. And if you're able to attend that, then that would be fantastic. Do look at the course website for the expected date for that, and we'll have more information about where precisely it will be in the upcoming weeks. But essentially, what the remainder of this project asks you to submit photos that can be used for this purpose. Now, given the size of the class, we have 80-something students, and given that pretty much all exhibition spaces tend to have very limited space, we're likely only going to be able to select a small subset of the images that were provided to us. So to that end, we're asking you to submit 4 photos that could potentially be used for the exhibition. And of course, since these are such a small, limited quantity, we're hoping that each one will be very unique in whatever form of uniqueness you want it to take. And it should also be very representative of your best work. I mean, we're only asking for 5 images here. And so we're hoping that you will take the 2 weeks to its fullest and be able to capture your best work that is representative of your best and submit it to us. More details on the exhibition will, of course, be forthcoming. But do look at the project spec for additional requirements for these images. In particular, one of the important things to note is that one of these 4 exhibition images can actually be an image that you have taken in the past. It can be for the purposes of this class. It can be perhaps your favorite image outside of this class, but only one of the 4 can be from the past. It doesn't have to be if you don't want it to be. If you want to take 4 unique images, 4 new unique images, that's great. But we can, if you want, use that one in the running as well. And the other 3 should, in fact, be new and taken for the purposes of this project. So do be sure that you go out and take some photos. There is a loose theme that we've associated with this, and it's somewhat ill-defined, but we do want to sort of focus your efforts on the local environment. So because we have a lot of students from afar, we're very interested in seeing what your environment is like, what it's like for you in your particular region. And so it doesn't necessarily have to be of your house or a park outside, but just something that sort of encapsulates that theme of your local environment. So for those of us local here, it could be something at Harvard, it could be something around your own home or perhaps in one of your towns. It doesn't really matter so long as it sort of encapsulates that idea of the environment. All right, any questions about the project 4 or project 3 or anything along those lines? All right, so I noticed that we have just perhaps due to the rain, just a little bit lower number of people in here. So we may be leaning upon the online discussion just a little bit more than usual for questions if you do have them. All right, if there's no questions, let's move on to dynamic range. So a couple of weeks ago, we talked very briefly about the idea of dynamic range and what that actually means for our images. In particular, we use this analogy that an individual pixel on a sensor is kind of like a rain bucket. And photons, the light that we're actually capturing, is like rain. And as that rain falls down in our bucket, we capture it. And eventually, when we actually complete the exposure for our image, we measure the amount of light or the amount of rain in this bucket and use that to determine what value, what exposure, or what value that pixel should actually have. We talked further about we tried to really stretch this analogy a little bit and tried to further this idea a little bit more by talking about, well, imagine we have a large array of these pixels. We have perhaps 2,000 buckets by 3,000 buckets in a huge array outside, and it's really through this that we're able to sort of detect variations in the rains, so-called, and determine our final image. But what happens, of course, if we try to take a capture when there's too much rain, so perhaps like today, which there's a, perhaps not yet, but should be a fair amount of rain coming pretty soon. If we were to have a bucket outside, what happens if that bucket actually overflows? So in other words, what happens if we capture too much light in this particular pixel is that it can, in some cases, actually spill over to neighboring pixels as well, very much like a bucket would spill over to neighboring buckets, and actually impact the exposure of those neighboring pixels as well. And we can get this idea in a word called blooming. So when we get blooming, it's some very bright point source of light that actually spills its light across to neighboring pixels. And really, that's as far as we can kind of take this analogy, but it's a pretty good one, and it's one that you'll see repeated quite often, particularly if you continue researching this sort of idea online. So there's a way that we were able to quantify this, and not to be scary, but this is just a very simple division, and this is one alternate way of thinking about dynamic range, and it fits very well with the prior analogy as well, which is that the dynamic range really is the division of the biggest possible signal. So whatever the highest possible quantity of our full bucket happens to be, divided by the smallest detectable signal. And I was trying to make the point a couple of weeks ago, and I want to hammer it home again now, that this smallest detectable signal really makes a big difference when we're talking about dynamic range. So if we were to imagine, if we go back to our bucket analogy for just a moment, imagine that we are able to have a bucket that can capture let's say we're just going to use a ruler to measure the amount of rain that actually falls within our bucket. And so let's say that it has a maximum of about 10 centimeters worth of rain that this bucket can actually capture. But if our ruler only has markings on it in only centimeter spacings, what happens when we get very low quantity of rain is that we really can't tell if it's 0 or 0.5 or 0.25 or 0.75. We have to round it either all the way down to 0 or all the way up to 1. So we would say the dynamic range of this bucket, so to speak, is just a value of 10, as it happens to have a dynamic range of 10. But if we were to able to increase the resolution of our detection, so let's say that rather than have markings every centimeter, we instead have it every half centimeter, we then double our dynamic range, and so on and so forth. And this matters very much in our discussion of digital cameras as well. If we were to talk about this in more concrete terms, there are electronics that actually read the signal from the pixel to try to determine how many photons were captured at a particular pixel. And the better that those measurements can actually be at detecting the number of photons, we can, in fact, make the smallest detectable signal even smaller and increase the dynamic range of our camera. Another way that we can increase the dynamic range would be to make the full bucket even bigger. So there's a variety of ways that we can, in fact, change the dynamic range in a camera. And we'll talk more about this in just a moment. Now, this is important because when we're talking about dynamic range, it's really talking about the range of tones that we can capture within a scene. And the vast majority of scenes, as you might recall, don't actually have a tonal range that fits within a very narrow slot, especially when we're talking about outside or very uncontrolled situations where we're dealing with harsh sunlight, where there might be areas of the image that are very harshly lit and other areas that are very in deep shadow because of any shadows that happen to exist within the scene. And so it really is the case that we can say that just simply due to physics, that larger sensors tend to have better dynamic range than smaller sensors. And this is oversimplifying it a great deal. We could also say it in another way, that larger pixels tend to have better dynamic range than smaller pixels. But again, that's also oversimplifying it. But these are each ways of thinking about how we can improve the dynamic range within our cameras and be able to capture more tones within the scene. It tends to be better for us as photographers to capture more tones when we actually capture the image so that we have more data to work with, so that we can actually edit the image to represent the scene as we wanted it, as we want to represent it. Perhaps we could increase the contrast a little bit and it will decrease the apparent dynamic range, but still we get that choice, whereas before we didn't necessarily have that choice. Now, dynamic range is important, and as you'll find out, when we talk about the differences in sensor sizes, it also will impact a variety of things, not just dynamic range. So digital cameras can come in a wide array of sizes. At sort of the biggest, the most expensive, we would have what's essentially called a medium format sized sensor. And these are enormous in comparison to some of the sensors that we would find in our typical digital camera, and especially in our camera phones, our iPhones or smartphones. So just as a comparison, the beige box in the center of this slide is representative of a medium format sensor. And all of the others are to scale compared to that size. So the next smaller one is this full frame, which is in fact sort of the largest that is within reach for us, for those of us that don't necessarily have tens of thousands of dollars to spend on a medium format camera. We might be able to, however, achieve with some expense, purchasing a camera that is in fact full frame. So there's a couple that I do in fact want to point out. There's some smaller ones from the full frame. There's APS-H, which Canon uses. It's the size that Canon uses exclusively in in only a very small subset of their cameras. The vast majority of digital SLRs tend to be APS-C sized, which are these yellow and green rectangles respectively. And now notice the difference in size between those and their full frame cousins. It is in fact significant. It almost appears to be a quarter as much. It's not quite that bad, but there is in fact quite a difference between all these. If we go down to the red one, this is the micro four thirds system. This one is in fact actually a quarter the size of the full frame sensor, but we can get even smaller than that. 2/3 of an inch, 1/1.7 of an inch, and so on and so forth. It's actually important to realize additionally that these small sensors, or maybe it's not important to realize, but it's just sort of as an aside, these small sensors have measurements that don't seem to make much sense if you were to actually look at the raw measurements of those sensors. It just so happens to be used as a convention against some old tube-style sensors that old TV cameras used to have. It used to measure the diameter of these tubes where the sensor was actually a little bit smaller than that. So just because it says 1/2.3 inches doesn't necessarily mean that is actually the size of that sensor in terms of diameter or height or width. It is in fact a little bit smaller than that. So if you do have a camera with one of those sizes, don't use that necessarily as a guide. Look at the actual measurement of the sensor. Usually it does, for every camera, will probably give you some way of being able to determine the actual true size of your sensor. And this is important for a couple of reasons, one of which is this dynamic range, but also, as you'll see in just a moment, it has a great impact on our apparent field of view when we attach some lenses to the front of our cameras. So I do all this not to ask you to memorize the fact that we have all of these different sensors, but really to point out the vast array of sizes that are available on the market. It's very difficult to predict which you might have, actually, because especially as of late, the past few years, we've been seeing smaller cameras actually have bigger sensors within them, which is a great trend, in my opinion. So we've actually seen, whereas before, even just a couple of years ago, APS-C size sensors and full frame sensors were the realm of digital SLRs. We now see a couple of compact cameras, in other words, cameras that normally have compact camera appearances to them, actually have sensors that are that large as well. So let's talk a little bit about pixel sizes in comparison to some of these sensors. So let's just take two theoretical sensors. On the right, we have an APS-C size sensor, which, as you recall, is smaller than full frame, but still relatively large compared to the vast majority of sensors that are out there. And let's say that it is about 6 megapixels. And on the left, we have a sensor that is considerably smaller. It's of sensor size 2.5 inches, but the actual true dimensions are given in millimeters here. And that is also 6 megapixels. So we can actually compute an approximate size for each of the pixels in these sensors. So I'm going to assume for just a moment that the aspect ratio of these is 3:2, where we have a width that is 1.5 times that of the height. In other words, we have a ratio of the width to height of 3:2. This is a typical aspect ratio for digital SLRs and large framed cameras. However, smaller sensors tend to have a different aspect ratio of something like 4:3, which is a little bit more square rather than wide. But for now, we're ignoring that, and we're assuming that both equally have an aspect ratio of 3:2. That actually simplifies this a little bit, because we can then say, okay, well, assume that we have a width of about 3,000 pixels. We have 3,000 pixels along the bottom, and we have a height of 2,000 pixels. If you multiply 3,000 by 2,000, you realize that gets you 6 million, which is precisely the value of 6 megapixels like we were just discussing. So basically, these have the same number of pixels, but obviously the pixels in the left are going to be far smaller than the one on the right. If we actually do the math and we realize that we have 24 millimeters divided by some number of pixels, so on and so forth, we get a size of, well, it's very, very small, but it's 8 microns. So we can actually do this. You don't have to worry about memorizing this. We're just doing this to understand a little bit better the differences in size between these pixels. So I've converted the millimeters, 24 millimeters, to meters in this case. So 0.024 meters divided by 3,000 is, and there's a lot of zeros here, 0.12345 meters, or 8 microns. We can do the same thing for the one on the left, and we realize, I'll spare you the math there, but the pixel size of that is 2.3 microns. Now, just for comparison, the thickness of an average human hair is generally quoted at about 100 microns. So what we're talking about is individual pixels that are so much smaller than the thickness of the average human hair. You could fit an enormous number of these pixels within the width of one of those hairs. So why is this actually important? Well, realize that we are talking about an area of pixel that is actually capturing light. You might recall that one of the aspects of exposure values that was really important is the F number, which is a ratio that describes the diameter, essentially, of the aperture, the amount of photons that are allowed to enter through the glass, through the lens. And what this actually means was that as we decreased the size of the aperture, less light, fewer photons were actually entering through the lens and reaching the sensor. So there's something of we really don't want to call it an analogy. It's not the same thing to say that smaller pixels inherently get less light, but there are, in fact, certain cases where this is true. Imagine that we have a lens let's say that we have two cameras. They are otherwise identical, except that one of them has the sensor on the left and one of them has the sensor on the right. Now imagine that we put a lens in the front of this camera. It doesn't matter what the lens is. You can imagine any lens. But imagine that we have the same lens on top of both of these cameras. Now there's a couple of ways that the image between these two cameras will actually be different. One of them is that this one on the left is actually only going to capture a very small percentage of the actual image focused by that lens onto the back of the camera. But the other one has to do with the differences in size of the pixels. When we're talking about pixels of size 2.3 microns, we're talking about a pixel that's almost a quarter the size of the one on the right, which means that these pixels, an individual pixel on the sensor on the left, is getting how many stops less light? Approximately. If it's a quarter, the amount of photons are actually hitting that. So one stop would be a half, and then another stop would be, a quarter. So a 2 stops reduction in the amount of light at each individual pixel. So why does this matter? Well, realize that one way to think of it is that the electronics on the sensor on the left now have to work harder to try to capture and try to measure those photons. And this is, in fact, an important reason why smaller sensors tend to have worse performance with their light gathering capability than larger sensors. All other things being equal, they are in fact receiving less light than their bigger sensored cousins. Now this, of course, is again an oversimplification, because there are some things that do actually make this problem not quite as bad. We'll talk about that in just a little bit. But keep this in mind, how smaller sensors with smaller pixels, with all other things being equal, have this problem of gathering much less light. So another way to think about this is if we go back to our discussion about dynamic range, the full signal, the full possible signal of our bucket that's about a quarter of the size is necessarily going to be less. So even if the electronics are the same, the dynamic range of the sensor on the left is not going to be as high as the dynamic range of the sensor on the right. But there's another way that actually you will notice a lot more quickly that the images between these two cameras will actually be different. So I want to show you this slide that from a few weeks ago, where you might recall we were using this as the discussion of perspective and how to actually change your perspective in terms of the way that we want to discuss it, you actually have to change your distance to it. You can't actually just zoom in on something and assume that you've changed your perspective, because essentially all you're doing is cropping that image. So just to go through this again, just to remind you about what was going on, we took an image. In this case, somebody took an image of a salt and pepper shaker sitting on a table at some distance away with a 33 millimeter lens. And then they took the center portion of that image, they cropped it out and blew up that image to now be the same size. And that's the upper right image. So those red lines sort of represent what we just did with that alteration. And if you look closely at the slide, it's kind of difficult to see in person, but especially if you're looking at it online, one of the things you may notice is that the quality of that has dropped significantly. What we did was a digital zoom, essentially. And if you have a camera that allows you to use digital zoom, realize that all you're doing is this. You're not actually increasing the magnification power of your camera. All you're doing is allowing the camera to take a crop and then blow it back up to larger size. This is generally not a good idea. I generally recommend turning off the optical zoom, or rather, not the optical zoom, sorry, turning off the digital zoom on your camera and just do it later, because generally more advanced software like Photoshop will do a better job of actually interpolating those pixels and actually making that image bigger. So don't let your camera do it later yourself when you have a little bit more control over the quality of that enhancement. Anyway, coming back to this, we have a 33 millimeter shot. We've cropped it. That's the one on the upper right. But now we've removed that lens, put on an 80 millimeter lens, taken another shot. And you can see the differences and the similarities between this shot taken with the other lens compared to the one that we had cropped. It looks like the same field of view. The perspective appears the same, but the difference is that because we've done an optical zoom, we have, in fact, a much higher quality rendition of that same image. So the very last one was the point that we were trying to make. If you actually want to change your perspective, you change your focal length back to 33 millimeters and actually move closer to those salt and pepper shakers, and you can actually see the distortion that occurs as a result of that movement. But it's this idea between the crop and the actual changing of the focal length that I want to bring to light again. Imagine that we go back to this scenario where we have two cameras that are otherwise completely identical, except one has a smaller sensor than the other one. Well, a lens that you actually attach to the front of one of those cameras is actually going to project an image into the camera that's circular. So of course, because our sensors are rectangular, the images that we see come out rectangular, but the lens is circular, and it doesn't really care about its particular orientation, so it will always project a circular image. So this is a representation of a fictitious lens that's held away from the screen and projecting an image onto the screen. And there are two boxes here, a red box and a blue box, representing two different sensors that capture the scene emitted by this lens. Now in this particular example, assume that we have a lens, so it's very similar setup to the one that we were just discussing. We have now a large sensor camera that's able to capture more of the field of view provided by that lens, and we have a smaller sensor camera that essentially takes a crop of the center of that lens. Now, if they are the same megapixel, and you view those images side by side on your computer at the same size, what this essentially appears to have done is to increase the focal length of your image. Right? So it's to tie this back to this prior thing, it's as though we have in fact used a higher focal length lens because we have the same number of megapixels. It's as though we've used a higher focal length lens by using a camera with a smaller sensor and assuming that it has the same number of megapixels. So what this really means is that we can talk about different sensor sizes in terms of their crop factor. So there is some factor that describes the difference in the size of a sensor compared to some reference that actually talks about how it will alter the apparent fields of view of a lens with a given focal length. So another way to think about this is that if I have a lens that projects this particular image onto a full frame camera, which is this red box. And then I remove that lens and put that lens onto a camera that has an APS-C size sensor, which has a smaller sensor. It actually appears as though I'm using a larger focal length than I actually am. Now, it's important to realize that we're not, in fact, changing the focal length of this image. The focal length is actually a physical measurement having to do with the camera system as a whole, in particular the lens, and the focal length indeed remains the same. But we can think of it as if we have, in fact, put on another lens with a larger focal length. So we can think of it in terms of an apparent focal length, or any sort of term that conveys that idea. And this is really important when we're talking about digital cameras, much more so than when we were talking about film cameras, where there really were a very small number of different sizes of film. There was the 35 millimeter film, and then there was that, oh my gosh, I can't even remember the size. The little cameras had it with the, no, I can't even remember. There were only a couple of different sizes, but in digital realm, we have a large number of images that actually, or rather, large number of cameras that have this different quantity of sensor sizes. So you might hear this term in a couple of different ways. You might hear crop factor, you might hear focal length multiplier, you might hear some other number of terms, but so long as they're referring to this same idea, realize that this is exactly what it is that they're talking about. APS-C tends to have a focal length multiplier of about 1.6. I suspect that for most of you with digital SLRs, that is probably the sensor size you have, unless you really splurged a bit and went for the full frame. If you happen to be using a Micro Four Thirds camera, it has a very nice focal length multiplier of 2. It makes it very easy to do that multiplication and figure out the apparent size, the apparent difference in focal length. Now, what this difference actually means is that you can take this APS-C size sensor and multiply the focal length of that, real focal length of that lens by that value, the focal length multiplier of 1.6, and you get the approximate, or rather you get the apparent focal length of the lens that you had used to capture that image. So in other words, let's put some numbers behind this. Let's say that I had captured this photo on the left with a full frame camera at 50 millimeters. What that would mean is that if I then took that same lens and in the same situation and replaced the camera with one that has an APS-C size sensor and took another photo, it would look like this. You notice that it looks a little bit more zoomed in, but the apparent focal length is now 50 times 1.6, or about 80 millimeters. So another way to think about that is if I then, just like in that slide a couple of moments ago, if I then took my full frame camera, put an 80 millimeter lens on it, I then capture the same field of view as the one on the right. So we need some sort of reference to talk about these particular things, and the vast majority of the time you will find that we reference the full frame camera. The full frame 35 millimeter camera is the sort of reference for the field of view that we are discussing here. So if a field of view for a full frame camera has some particular, allows some particular amount of the scene to actually be captured by the camera, then we generally talk about the field of view multiplier to decide what the focal length on our smaller censored camera needs to be in order to capture the same field of view. So this is, you might, depending on the way that you take photographs, this may be a good thing. If you like to take sports photographs, for instance, or wildlife, or something that tends to be where those objects tend to be farther away from your camera, then perhaps you might actually enjoy this idea of having a small sensor on a camera with a relatively high focal length, because it's as though you get a larger lens for free. It's as if you have a lens with a much larger focal length attached to that particular camera. But what this also means is that at the opposite end, at the wide angle end, we now have a much bigger problem. Because if we put a wide angle lens on our full frame camera, let's say we put a 16 millimeter lens on our full frame camera on the left, and let's just assume for a moment that that's the widest possible lens that we can get for our full frame. I realize that there's probably some distinction between systems and such, but that's pretty common wide, ultra wide angle focal length for a full frame sensor. Now, if we actually remove that and put that on our cropped sensor, what this means is that it's not quite as wide as we expected. It's 16 times 1.6, and what would that be? It's about 25, 26 millimeter focal length apparent on that cropped sensor. So you're really missing out then on this additional field of view that you may have wanted by purchasing a wide-angle lens. So what this means is that for smaller cameras, or rather for cameras that have smaller sensors, these manufacturers also need to release lenses that have smaller focal lengths to try to achieve the same field of view that you might get in a 35 millimeter camera. So this is why that we can't really use the same lens on all of these different cameras. I mean, first of all, the lens might just be, humorously large compared to the size of the camera, but also this idea will bite us. We can't actually take one of these lenses, and because of this crop factor, we will actually lose out on some of the width of our lenses in terms of the field of view there. You might hear, especially for digital SLRs or for Nikon cameras in particular, that there's this concept of digital lenses. Digital lenses aren't necessarily digital, but they are, in fact, meant for these digital sensors, which tend, especially up until only a couple of years ago, which tend to be much smaller than the full frame 35 millimeter sensor. So what does this actually mean for us? How does this actually impact our photography? Well, many of us probably don't have cameras that have full frame sensors. So it's useful for us to talk about field of view by converting our lenses to their apparent focal length, or their apparent fields of view, or their effective focal length is another way to say it, with regard to their 35 millimeter cousins. So on the left is a Panasonic Lumix, which is now several years old, but it has a very, very small sensor. In fact, it has that the sensor from that slide a couple of minutes ago, that with the very, very small pixel size, 1/2.5 inches the size of the sensor. But we can see, if we take a look at the focal length of this lens that's actually embedded within the camera, it's 6 millimeters to 72 millimeters. And that, of course, doesn't tell us very much about its apparent field of view compared to a 35 millimeter camera, unless we take its focal length multiplier and multiply those values by that multiplier. It just so happens that they've done that calculation for us on the side of the lens barrel. We can see that at the widest, this camera gets to be an apparent field of view of about 36 millimeters, which is considered wide angle, but not ultra wide. It's about the same field of view that you would get in a typical smartphone camera. And at the opposite end, at the long end, it goes to an extreme 432 millimeters. This would be an enormous, enormous lens if we were to purchase a 400 millimeter lens for a full frame camera. We're talking about many thousands of dollars. We're talking about huge. It's very conspicuous. It's very heavy. There's a lot of downsides to it. But there is an upside to that lens over this one. So even though we get this enhancement in this focal length, we can really zoom in with this lens, whereas we couldn't necessarily to that degree without great expense on the 35 millimeter side. We do get bitten by this problem that this camera does have a smaller sensor and therefore probably has lower dynamic range, therefore probably captures light not quite as well as its larger censored cousin might be. So this is the trade-off. Smaller sensors give you a little bit better portability. It makes it possible to really carry around a larger range of lenses that have a lot of field of view capabilities that perhaps the larger ones could not. They tend to be a little bit less expensive because building a sensor that is very small is much cheaper than building a sensor that's very big. There's a lot of reasons that we would want to do this, but generally speaking, the larger sensors will give us the much higher quality, the much better quality that we would hope for out of a high quality digital camera system. So on the right is just a sample of an Olympus lens that is from a Micro Four Thirds camera, and it has a focal length, a true focal length of 7 to 14 millimeters, with an apparent focal length or an effective focal length because of the 2x multiplier on the Micro Four Thirds system, an effective multiplier of about 14 to 28 millimeters, which would be a very ultra wide lens on that particular system. All right, now let's come back to this idea that we had just talked about a couple of minutes ago, where we had these two different sensor sizes. One of them was APS-C on the right. One of them is the much smaller sensor size, the 1/2.5 inch on the left. And now let's actually try to change their megapixel count so that the pixels are actually about the same size. In this case, after we do some of the math here, we realize that the image, if we were to keep the same megapixel count of 6 on the sensor on the right, we do some math and we figure out that to keep the approximate same pixel size on the sensor on the left, we need to decrease it to about 0.5 megapixels. So it's really now as though we've taken out the very center portion of this image, or rather of this sensor, this bigger sensor on the right, and we're now using it as a standalone sensor. Now let's do that same thought experiment from just a moment ago, where we have two cameras that are otherwise identical except for these two sensors, and we have a lens that is identical on top of both. So what now is the difference between these two? Is it that this smaller sensor is now getting less light than the one on the right? So I just made the argument that the pixels are the same size, so the answer is no. They're in fact getting at each individual pixel with everything else being the same. The sensor on the left is in fact at each individual pixel getting the same amount of light as the sensor on the right. But the difference now is spatial resolution. We've lost an enormous amount of resolution on the left. We're just cropping out the center portion, and that's it. All other things being equal, it's as if every time we took an image with this, we just threw away everything but the very center portion of this image. So why is this matter? The reason that this matters is that we generally don't want to design digital cameras in this way. We generally want to design digital cameras that are smaller versions of their bigger cousins. So what this means is that not only do we have to decrease the size of the sensor, but we also need to decrease the size of the pixels so that the megapixel count can remain approximately the same, so that we still can get a good amount of resolution from those cameras that have these very, very small sensor sizes. But that also means that in order for us to get the same field of view that we can with these larger sensors, we have to shrink the focal length of the lens that's on top of this particular camera. But that also means one other thing. Imagine all of the exposure values that we had talked about in prior weeks. One of them was shutter speed. The shutter speed doesn't really change anything when we're talking about one sensor versus the other, nor does the ISO. We'll talk more about what ISO actually means in just a little while. But the thing that does change is F number. And in particular, although we can have F numbers that are the same, we can have an F number of a lens on this larger camera be an F number of 2.8, and we can have a lens with an F number of 2.8 on this smaller camera. Realize that what this means is that because we have changed our focal length to get the same field of view, to get the same F number, we also have to change the diameter of that lens. Which means that the actual size of the aperture, the actual physical size of the aperture for an f2.8 lens on a camera on the right versus an f2.8 lens for the one on the left that has the same field of view, which means that the focal length for the one on the left is much smaller to get the same field of view as the one on the right, the aperture of this is going to decrease by a similar amount. The actual diameter of the aperture is going to have to change by a similar amount. And the end result of this is that we actually do then get less light. And this is kind of I don't want to say that, it's sort of an interesting thing, because when you actually change the focal length, you actually are increasing the amount of light that this sensor gets. So the oversimplification that I had made in the past, where we were looking at both of these sensors in the same megapixel count, we were talking about how if we put the same lens over both of them, that each individual pixel on the sensor on the left was going to get less light. That was certainly true. But what we lost in that case was the angle of view in the camera on the left. So now that we've shrunk the lens so that we can actually get the same field of view, we actually are collecting more light. It's sort of an interesting phenomenon that by shrinking the lens, we're increasing the amount of light by some amount. But what the result is in the very end is that we are in fact impacting the amount of light because of the size of the aperture, the actual real physical size of the aperture, not just the ratio, not the F number. The actual physical size of the aperture is actually different now on this shrunken camera from the one on the left. So there's multiple ways to think about this. We can think about it in terms of the spatial resolution, or the resolution really that we're capturing with these cameras. We can say that we have a sensor on the right, this exact slide, we have a sensor on the right with very high megapixel count. We want to preserve all of the light gathering capability of those pixels, so we just crop the center portion of that sensor out, and then we capture an image with that. But we've now lost the resolution that we might have gained by actually shrinking all of those pixels. On the other hand, we can actually decrease the amount of signal that we can receive by taking this sensor and actually shrinking it so that all of the pixels are also smaller. We've now increased the amount of resolution, and by changing the size of the focal length, by changing the size of the lens and by changing the focal length of the sensor on the left, can we then actually get the same, capture the same field of view and capture the same number of megapixels for that scene, but now we have in fact changed the size of the aperture on that lens, even though the F number remains the same. So don't forget that the F number is a ratio, just like we talked about, and because we've changed the focal length, we also have to change the diameter of that aperture to maintain the same F number across these two. Okay, let's let that digest for just a couple of minutes. Take a 5-minute break, and when we come back, we'll continue talking about sensor size. Okay, welcome back, everybody. So I realized over the break, thanks to Shelley's reminder, that I did forget to mention an important thing with regard to Project 4. And in fact, not only did I neglect to mention it when I was describing Project 4, but I also neglected to mention within Project 4 itself. So the specification isn't any different than as it is online, but there is one other way that we are hoping to use the image that you submit to us in the first section, the section for the website. So you might have seen, particularly for those of you that watch from home, the first 10 seconds or so of the video are actually a collection of photos that are, for now, pulled from the website. And so included among those, as soon as we start to get some of these images for Project 4 with regard to the website, we'll also start to use those within the video as well. So your photos will actually get quite a bit of exposure, not only on the website, but also on the online videos. And so we generally have a wide number of photos that are actually visible within the video, but then there's sort of like a title photo that's actually displayed. Because we only have a small number of lectures left in the class, there will only be a couple of those photos that we'll be able to pick. But still, it's still a neat way for you to enhance the exposure of your particular photographs. So do be sure to work hard on those, and please give us the best possible photos that you can. I did also want to announce one other change that is relatively minor, but still wanted to mention it compared to the syllabus that was posted a couple of weeks ago. In the past, We had planned to do, after this sequence of 2 digital cameras lectures, so this one and then the second one next week, we had planned to do a lecture on colors where we talk a little bit about color calibration, white balance, and all of the technical aspects behind that. But due to a conflict, I actually will have to swap that for the lecture that was actually going to be following that. So it's just a small lecture swap, and this has no true impact on you other than that really it might be slightly different from your earlier expectations with regard to the schedule there. And in fact, the From Stills to Video lecture I'm very excited about because it will be led by not me, in fact, by the staff Shelley and John, where they'll get a chance to talk about their experience with video. All right, let's go back to talking about digital cameras. Now, I fully understand that this is, what we've been talking about is a little bit difficult to wrap your mind around it. So do try these same thought experiments that we've been alluding to in the past. Try them for yourself and see if you can sort of figure out weird corner cases or weird ways or weird things that are actually a little bit different. And do ask us questions if you have any. But just think about how the physics of these things has to change if we actually shrink all of the components within a digital camera, but try to maintain the same resolution. And it's actually a result of this that causes sort of a very common, what would be, what we could say is a myth in the realm of digital photography, which is the idea that the size of the sensor, and more generally the size of the camera, limits the amount of depth of field that we can get out of it. And it's not really accurate to say that smaller cameras have a different set of, have different rules for the depth of field compared to their larger cameras. What's more accurate is to realize that larger cameras actually have a superset. So they actually have capabilities that include the depth of field of the smaller cameras. And the reason for this is actually because of all of the things that we've been talking about up until this point. So this is an example from a wonderful site that actually goes into a lot of the really nitty-gritty, low-down technical detail about digital photography called clarkvision.com. But this example is actually, I think, particularly useful when we're trying to figure out this aspect and actually trying to tease apart why it appears that smaller cameras tend to have much larger depths of field than bigger cameras. So we have here 3 photos taken with 2 cameras. In the middle is a photograph that was taken with a compact camera. All of these cameras are pretty old now, a few years, but the same ideas actually still stand with modern cameras these days. In the middle we have a photo taken with a compact camera with a very small sensor. And on the top and on the bottom, we have photographs taken with a full frame sensor, or at least a sensor that's considerably larger than that of the middle camera. Now I want you to notice a couple of things. First of all, they're all exposed the same. Or at least, I mean, there's maybe minor variations, but not really perceptible in my opinion. They're all exposed very, very well the same. The other thing to notice is that they all have the same field of view. They all have the same amount of this ruler actually captured within the photograph. The difference between these is the exposure values to actually capture these, but also the very apparent difference is the depth of field. That's actually different from the bottom camera, or rather the bottom photograph, compared to the top 2 photographs. Now there's one more thing I want to point out, which is very important to this discussion, which is that even though the top 2 images were taken with different cameras, one of them is a compact camera and one of them is essentially, we can think of it as a full frame sensor, even though I don't think it is. I think it's APS-C. But we can think of it as full frame. We can think of it as a much bigger camera. Realize that the depth of field is, for all intents and purposes, identical in these 2 photos. Now recall what I mentioned just before the break, which is that if we have a camera that has a large sensor and has a lens on it that gives us an apparent field of view, Now we want to shrink that camera to be much smaller, but still have the capabilities of actually capturing the same image. Then we have to shrink the sensor, even though we perhaps want to keep the same number of megapixels. We also have to shrink the lens so that the focal length is smaller to capture the same field of view. But that means that we also have to shrink the size of the aperture itself. So what's interesting about this is that these two photos, and this example works particularly well because these photos were taken with sensors from the same generation of electronics. So what that means is that one camera is not significantly newer than the next. And also, it just so happens to be that they're both the same manufacturer of cameras. And so really this is as close to isolating all of the variables as we possibly can. The technology with regard to the sensor is probably pretty similar, even though the more expensive camera probably has higher quality electronics and some other things. But still, we've sort of eliminated a lot of these variables. But realize that when we have a particular field of view, for this camera in the middle here, we had to have an aperture of a certain size, which is going to be, because everything else shrunk, is going to be very small compared to the f number, which might be the same for this bigger camera here. So in fact, realize that that is the difference between this middle and this bottom image, is that even though we have the same f number, f3.5 for the bottom image and f3.5 for the middle, it appears as though the depth of field is much larger for this middle image. But the reason for that is that the aperture of the camera down below was much bigger than it was for the camera that is in the middle. So if we actually change the size of the aperture, if we actually compute the difference in the size of the sensor between these two cameras, and that was some value like 2.2 or something like that, and we actually compute what the difference in the f number would be to account for this difference in size. So we actually increase the f number to make the diameter of the aperture smaller in this bigger camera, so that in the end we have now two cameras that have, one sensor is very big, another sensor is very small, they have the same field of view, but now the apertures are exactly the same size by this multiplier. So now if we use a value of f13, do we actually get equivalent amounts of depth of field? So it's not the case. It's really not accurate to think of smaller cameras as having inherently larger depths of field. You can, in fact, get your larger camera to have a very large depth of field as well by changing the size of the aperture, just like you would just like you would have to do to shrink the size of the camera to be much smaller. But there is one other difference. If you think back to our days of exposure, if I were to actually change the f number to be much larger to try to achieve this much greater depth of field, the photograph, of course, would be much darker because I've reduced by a vast number the amount of photons that are actually entering into this particular camera. So not only that, but I also have to, so what this means is that I have to change one of the other values, either the shutter speed or the ISO. In this case, this was very well done. Another reason this example was very well done, because in this case, he didn't alter the shutter speed of this image. It is in fact 1/8 of a second at the very top image, just like it's 1/8 of a second for this middle image, which means that the same number of photons are actually flowing into the camera. But what changes now is the ISO. So we have to use a much higher ISO in order to capture the same number of, or rather, in order to get the same exposure that we would. So this hints at something else as well, which is important here. Really, what is the distinction between the smaller camera and the larger camera is the size of the aperture, but also there is a criterion for resolution. So in other words, because this bigger camera may have had bigger quantity of megapixels, or perhaps it didn't and it had bigger set of bigger set of pixels. What this essentially means is that we now have to decrease the signal just slightly so that we can sort of match the signal to noise between the upper camera and the lower camera. So these two images are, for all intents and purposes, the one above and the one in the middle, nearly identical, or as much so as they possibly can be with regard to these two particular cameras. So again, the major takeaway when we're actually talking about these different size cameras is that it's not necessarily accurate to think of smaller cameras as having larger depths of field just by nature, but it is in fact a subset of the capabilities of bigger cameras, which can in fact alter their settings, use a smaller physical aperture size to actually capture the same depth of field as those other cameras. Any questions on that? I realize that the distinction is subtle. So it is one, though, that is somewhat important when we're actually thinking about cameras, especially cameras that you actually want to purchase. When you are thinking about a camera purchase, realize that the smaller cameras with the smaller sensors, and with what we're talking about really is the smaller sensors, means that in order to have the same field of view, we have to shrink the size of the lens itself, and this impacts us in a wide variety of ways. Yes?
Dan, would you mind just one more time going over how the depth of field is the same for those two, the top two, given different F numbers?
Mm-hmm.
If you go over one more time, I'm trying to absorb it.
Sure, absolutely. So just to rehash this same idea one more time, and maybe slightly different words, is that when we shrink the size of the camera, so we have here two cameras. We have a Canon 1D Mark II, which is going to have a really large sensor. We have a Canon S70, which is a compact camera, a very small sensor. As we shrink the size of the camera, in order to obtain, because of the change in the size of the sensor, because of this idea of a crop factor, in order to obtain the same field of view, we also have to shrink the lens as well. When we shrink the lens, we're changing the focal length of that lens, but we are also changing the size of the aperture. So remember that aperture, rather f number, is a ratio of the focal length divided by the diameter. And what this means is that if we change the focal length and if we change the diameter by an equal amount, then we are in fact keeping the same f number, even though the size of the aperture is now much smaller. So really what is happening when we're taking a picture with a specific depth of field is that it is defined by the size, the actual diameter of the aperture, more so than it is the size of the camera. It's really the major distinction here that we want to make. But because the bigger camera has the capability of actually shrinking its aperture to be the same size as the actual size of the aperture in the smaller camera, can we then capture the same depth of field in that big camera? But what this means, of course, is that by shrinking the size of the aperture in the big camera, we then have to increase the f number. And that's the distinction here. Is that a little bit more clear, I hope?
So is the top one then would be cropped to give the same image? You understand what I'm saying? So you had
So there's no cropping happening here. These two cameras were set up essentially next to each other, but the focal length of them were different, so that we actually were able to capture the same width of the scene. So because the smaller sensor, because of all the reasons that we had been talking about in the first hour, because the smaller sensor essentially crops out the center part of a lens, we then have to change the focal length of the lens in order to capture the same field of view. So there's no cropping in software happening here. They just happen to be, it's a result of this crop factor that we have to shrink the lens and shrink the aperture so that we get this result here. Okay. Now, for those of you following along at home, especially for the live stream, you'll notice that the slides actually end there, but I actually have a few more that I didn't post on the PDF, but I will do so after today. I wasn't actually sure if we would have time to get to some of these, so I'll update that later. Now, I do want to talk about how all of this stuff actually relates back to pixel size as well. This actually has a great impact on the quantity, just like we've been talking about before. This has a big impact on the dynamic range of individual pixels. So imagine that we have pixels that are really wide, very large, as we did in those examples of the large sensors that have 6 megapixels, for example. We might have pixels that are approximately this size. Now assume that we shrink that sensor so that all of the pixels also shrink, and we try to maintain the same number of megapixels so the pixels are actually smaller. We might get pixels that are this size instead. So realize that if we're actually capturing light, it takes fewer photons to fill up this pixel, this smaller pixel, as it would to fill up this larger pixel. Now, why does this actually matter? This actually alludes to this idea that we have an alteration in the amount of dynamic range that's possible between these two sensors. All other things being equal, the electronics being the same, the sensor type being the same, and so on and so forth, the focal length that actually would have to be the same for these, for all of this to, well, I guess the focal length would then be altered so that we have the same field of view, so we have the same number of photons actually flowing. What we actually see is that larger sensors with their larger pixels actually have a higher dynamic range than the smaller pixels as a result of smaller sensors. So what this means is that it takes fewer photons to fill up that well to be about the same amount in our smaller pixeled cousins. Excuse me. So once again, what this means is that because we have a smaller, biggest possible signal, the dynamic range for our smaller sensors tends to be not quite as good as our bigger sensors. Now there's an interesting impact of dynamic range here. When we're actually talking about ISO values, there's no actual physical change in the sensor itself. What actually happens when you alter the ISO values in your cameras, it's really changing sort of like the amplitude of the amplification of the signal. So another way to think about this, that if we were to go back to our analogy of full buckets, is that if we want to be more sensitive to small amounts of changes in the photons, in the number of rain that we're capturing, for example, we just recalibrate what happens to be a full bucket. So in other words, let's say that we increase the quote-unquote sensitivity. And you might recall when we were talking about ISO that I said that we can think of it as sensitivity, but that's not really what's happening in the camera. It's not really changing the sensitivity. This is what's actually happening. What's actually happening is that it's considering about half at an ISO value of 200 for a camera that has a lowest possible ISO of 100. It's considering ISO 200 to fill up the bucket about halfway and then just multiply those values by 2. So what this means is that you fill up the bucket halfway in ISO 200, and all of a sudden that's considered a full bucket, and that is considered the brightest possible value. Now this might actually seem very, very bad, because as you continuously increase the ISO, what this means is that fewer and fewer and fewer photons are actually going to be possibly captured by this sensor before it's actually considered to be a full value. And what this means is that we're actually decreasing the dynamic range as we increase the ISO on our cameras. So when we were talking about the impact of ISO on a camera, yeah, we got additional noise, but one of the things that we also had was a decrease in the dynamic range of our camera as we increase the ISO. Now, it's not quite as bad as it might look here. It's not quite as bad going from ISO 100 to 200 that we're actually having the dynamic range, or by that, yeah, we're not actually like having the dynamic range in this case, and similarly for 200 to 400. That's not actually what's happening, because it just so happens that through some fancy electronic tricks, that as we increase the ISO, the read noise actually goes down just a little bit. So remember that I talked about how the dynamic range is the biggest signal divided by the smallest detectable signal. So if our ISO 200 had a full bucket of half as much, it just so happens that the smallest detectable signal actually goes down just a little bit as well. So the loss of dynamic range is not quite as bad as it might seem by this halving of values in order to achieve this ISO. So another way to think about this is that at ISO 200, for example, the camera just looks at all of the values at a particular pixel and it doubles them. And what used to be a value of 128, if we were to think of this as a bucket from 0 to 255, so just like we've been talking about how individual pixels can vary in tonal range from 0 to 255, if we were to think of a half full bucket as a value of 128 and then double it, then we can imagine that anything that was above that will actually just be lost in values. And that is indeed what happens. But again, although we are in fact losing dynamic range as we increase the ISO, it's not quite as bad as actually reducing that dynamic range in half. Any questions on that? All right. So now that we have a little bit better understanding of what's happening in the camera, I want to talk a little bit more about sensors themselves. Realize that primarily there are two major types of sensors. There's active pixel sensors and there's passive pixel sensors. And each one of these has a wide variety of types, but the most common of those for active pixel sensors is CMOS type. And passive pixel sensors, the most common type is CCD. So even if you're not too familiar with these terms, you might have heard the term CMOS. You might have heard the term CCD if you just quickly browse the specifications for your camera. What we find is that a lot of digital SLRs in particular have CMOS type sensors, and a lot of compact cameras tend to have CCD. That's again an overgeneralization. You'll probably find some examples that do not follow that generalization, but that is in fact a good way of sort of breaking it down. So what it actually means to have an active versus a passive pixel sensor is to think about where precisely the light that is collected is amplified. In the case of the active pixel sensor, it happens at each individual pixel site. In the case of the passive pixel sensor, it happens globally. It happens for the entire sensor after it is being actually read off the sensor. CCD is really prevalent. Nowadays, CMOS is becoming increasingly more so, especially as the size of sensors increase. There's advantages and disadvantages to both. CMOS tends to be a little bit cheaper, which is why we find that in bigger size sensors, because it's much more expensive to actually build sensors that are bigger than it is to build sensors that are smaller. And so one way to cut costs is to actually use the CMOS type active pixel sensor in order to achieve slightly cheaper large sensor sizes. They do tend to use slightly less energy, which is one of the reasons why digital SLRs tend to have better battery life than compact cameras, is that the active pixel sensor tends to use less energy. But also it tends to have higher noise. But again, this doesn't really matter if the sensor, it doesn't matter as much perhaps, if the sensor is bigger and therefore the pixels are bigger, which allows it to collect more light, which allows us to have a better signal-to-noise ratio and to improve our dynamic range. However, the technology is catching up a bit with CCD. You do typically find CCD because of these other advantages, the fact that for the same, all other things being equal, it does tend to have better noise characteristics. What I mean by that is it actually tends to have better image quality. Even though you find these in sort of scientific situations and also for smaller cameras where we really do want to improve our noise characteristics in these small cameras, It does, I would say that really the technology doesn't matter so much anymore. I wouldn't buy one camera over another because it has CMOS versus CCD. I don't really pay attention to it, but it is interesting to note the differences between these two types of sensors. So, not to scare you, but here's an electrical diagram of what an individual pixel in an active pixel sensor actually looks like. So there's a variety of transistors here. You don't have to worry about what this actually means, but realize that there's a few electric components at every individual pixel site that actually allows us to capture the light. Now in this case we have a photodiode. This is a photodiode which actually captures the light. And then we have 3 transistors here which actually through some electrical connections allow us to measure the value of the photodiode as the photodiode actually collected the light here. So why am I showing this to you? Well, you don't have to worry necessarily about what this actually does, or you don't have to worry about why we have these electrical components here, but just realize that we do have these components, that we have for a given pixel quite a lot of area devoted to stuff that is not collecting light. We have space devoted to the transistors. We have space devoted to the connections between pixels and the electronics that actually read the data from those pixels. And what this actually means is that a very small percentage of the pixel site actually collects light. So what this means is that generally we have a big pixel. Let's just draw a pretty cheesy little diagram. We might have a pixel, and I use the term big loosely here because of course these are microns in size, very, very small fractions of a meter. And we might have a lot of electronics in this pixel, and only some small portion of it is actually used to capture the light that falls within that pixel. So this is bad, obviously. We have a situation here where we have a lot of light that might fall onto the pixel, but only a small quantity of that light is actually going to be read when it hits the photodiode, the actual electric component that actually is used to measure the amount of light that hits it. So how can we fix this? Well, it seems like one obvious way would be to make the photodiode bigger, but that's hard. We need this electronics. We need the electronics that actually surround this to actually have a working digital camera. So perhaps another thing that we could do is to in fact put a lens on top of this pixel and focus the light that falls anywhere within this pixel directly onto the photodiode. And that's precisely the technology that your camera actually uses. A pixel has a lot of layers that actually make up an individual pixel site, but one of the most important ones is this micro lens. Excuse me. And improvements in the micro lens can greatly improve the amount of light that is actually focused on that individual pixel and hits the photodiode. Any improvements in that mean that the photodiode can then register additional light, and you have an increase in the amount of signal, you decrease the amount of noise, and you improve the dynamic range, the light gathering capabilities. It's a big win. And this is where a lot of the improvements in digital cameras have come in recent years, is that the manufacturing techniques to actually create these micro lenses have improved to such a degree that the electronics themselves have not had to change that much, even though they have, but they haven't had to change that much to really improve the light gathering capability of sensors. Every so often you see an announcement from the big manufacturers like Canon or Nikon where they actually talk about improvements in their micro lens manufacturing, which now increases the amount of light gathering capability by about a stop or so. And it's actually really impressive every time that they're able to improve the amount of light that these individual micro lenses are able to focus onto their photodiode. But this also alludes to another issue that is very important to us as well. That is that imagine that we have light that's coming, it's light that is being focused from a lens doesn't always hit the sensor directly head on. If you have a wide angle lens, for example, it's going to, the focal length is going to be somewhat short, and so you will have light that actually comes and hits the edge of the sensor in particular at a very strong oblique angle. And having an improvement in the micro lens that can actually then take that light that's not coming head on and then refocus it to actually fall down into around all of these electronics and into the well, into this photodiode well that actually captures that light information is going to be a big improvement in the amount of light gathering capability. So really this term that I use, the well, is actually one that's useful and important when talking about this. You really can think of this as like a well. There's all these electronics that surround the photodiode. It's really like a well that we need to focus the light in order to properly record and capture that light in our circuit. Excuse me. Now, there's another interesting thing about this, though, and that is that you can see that there are a variety of layers associated with this pixel. We have the photodiode at the very bottom that actually records the amounts of light that's actually responsible for capturing the photons and converting that in combination with the electronics that surround it into an electrical signal that the camera can then read and interpret and store as an image. Then there's the micro lens as well, but there's another layer. And the reason that we have this layer is because of the somewhat sensationalist idea that digital cameras cannot actually record color. When I say that, these photodiodes have no way of interpreting individual color. It has no way of really knowing when some light that hits it is going to be red, or when some light that hits it is going to be green, or when some light that hits it is actually is blue. All it knows is that it has captured some light energy, and therefore it is going to vary its voltage. It's actually going to vary the electrical signal that it is able to capture. So these photodiodes are grayscale. They operate from black to white. And these cameras actually don't have the capability on their own to capture color. So there's another layer that actually does this for us. So imagine how we would actually have to try to do this. How would we actually be able to capture some of the color information at an individual site if our photodiode doesn't actually have the capability of recording this color? Any ideas? How can we do this? How can we try to get a photodiode to understand color if it can't? Maybe another way, and a hint towards this, is that maybe a photodiode shouldn't have to understand color. Maybe instead the camera should know, based on the photodiode's position, what color is actually being displayed, or rather being shown onto that particular photodiode. Any ideas? Yeah.
Is it the way different colors, wavelengths of different colors are bent by the lens, or?
Oh, that's actually, I like that idea a lot. So is it the way, so we had talked about so actually I don't think we've talked about it quite yet, but in a lens, wavelengths of light, different wavelengths of light, which correspond to different colors, will actually be refracted at different quantities, and so they will actually, sort of like when you shine a white light through a prism, it spreads the colors out a little bit. So is there a way that we could harness that information and use the micro lens and perhaps the position of the light in the micro lens to try to figure out the color of the light? That's a good idea, but that's not actually what's happening. This red layer is actually a hint to what is going on. In fact, what is happening is that at each individual photo site, do we have a filter? We have either a red filter, a green filter, or a blue filter, and that allows only those wavelengths of light to pass through the filter and be registered by the photodiode. So what this means in essence is that an individual pixel can't understand all of the three possible colors, or well, of the three colors, it cannot figure out the precise color that made up that location. But what it can figure out is the brightness of red at that particular location, the brightness of green at a neighboring pixel, and the brightness of blue at another neighboring pixels. These are separate pixels. One pixel cannot understand all three pieces of these color information, this primary color information that is used to make up our images. And this alludes to a further problem. There's issues of how do we recombine this information? Obviously our pictures, when we look at them full size, we don't see a pixel of green followed by a neighboring pixel of red, followed by a neighboring pixel of blue, and so on and so forth. We actually see the colors that made up that scene. There's another problem as well, and that is that our sensors are rectangular. They're not triangular. We have three colors here, but we have to have some sort of pattern on our sensor that allows us to have each of these perhaps equally, but still allows us to capture all of this information appropriately. So what this actually means, or how we're able to overcome these particular issues, we'll save until next week. So think about how we can actually overcome some of these issues, and we'll talk a little bit more about color filter arrays, the arrangements of these filters, and how we're able to use them and recombine them into the images that we see, and the impact that that actually has on our images. You may not even realize it, but our images are soft as a result of this problem here. And so with that, I want to thank you very much for coming, especially for those of you that really dragged through the cold, rainy night to attend this week's lecture. And have fun with Project 4, and I look forward to talking to you again next week when we talk about digital cameras continued. Thanks again.